Good evening. I welcome you all for the summary session for the course uh, Polymers, Concepts, Properties, Uses and Sustainability. So, in this live session, we'll just go through a recap of all these lectures, all the 12-week lectures, and also we'll also see some practice assignment problems. Now, let's get on to the session. Yeah. Let's go through the brief recap of all the lectures taken so far. Okay, recap of lectures of week one. So week one lectures were all based on a basic introduction to the course and to the uh, to the concept of what are polymers and its unique features. So the first lecture was on advantage of polymers, why polymers are ubiquitous, what makes it ubiquitous, surrounding us. So what are the mechanical responses, the ease of fabrication, and the cost and durability that makes polymers, these advantages makes polymers, almost, spread over wide range of applications. And what is the disadvantage of polymers? What are certain standard properties? What is the physical aging, thermostability related to polymers? And then the performance and sustainability issue related to polymers. And then what are some advanced application? So some examples were cited like plastic electronics, where even it is not just the case of the electronic, but even in the performance aspect, the polymers are being used in electronics, and then plastic solar cells, soft robotics. So these are some of the advanced applications. And then the course module was discussed, and the next lecture was on what are polymers and its unique feature. What are the description modules were discussed, and how to describe polymers. So what are monomers, oligomers, and the diversity of polymers around us? What is the functionality of a polymer, and how does what all makes up the molecular architecture of polymer? For example, a polymer will have a backbone, it may have a side group, a particular type of end group, and then the degree of polymerization may vary. They will have different, they may be branched or they may not be branched. uh, and then the next lecture was on the concept of what are the unique features of polymers. Here the process, structure and property correlation, what are the processing of polymers, what are different polymeric materials. For example, you have a polymer, there may be a core polymer, or there may be polymeric blend, polymeric composite, porous polymers, polymers with charge, and then what is a milk processing, shaping, curing of polymers. So these were all discussed. And what are the structures and properties of polymers? What are the states of interest? So polymers, you will have a liquid-like as well as a solid-like property. What are the associated properties? And how does a particular way of processing causes, leads to a particular type of structure or orientation of polymer molecules, or how does a processing affect the property, or how does the structure affect the property? So these aspects were discussed in this lecture. For example, processing, the biaxial stretching of BOPP, was discussed, and how does it helps in orientation, which is nothing but your structure, was discussed. So different aspects of these were discussed in this lecture. The next lecture was on a basic introduction to biopolymers. What are the different classification of polymers as such, based on monomers, and what are the common families of polymers, and what is a natural polymer, what are the related terms, like it may be a bio-based polymer like from natural sources. And then there was a brief discussion on natural fibers, like and then there was a discussion on polylactides, polyols, and then what are biocompatible polymers, biodegradable polymers, and then type of biomacromolecules, like based on the type and based on the origin. The next discussion was on, the property, especially the molecular weight. So, what is the effect of size? The effect of length of a polymeric molecule, branches, blocks, or cross-link in case of a cross-linked polymer. What is a monodispersity and polydispersity? Okay, and what is molecular weight distribution, and how can you really interpret those? And then discrete molecular weight distribution, continuous molecular weight distribution, how can you estimate? And then molar mass definitions, number average, weight average molar mass, viscosity average molar mass, Z average molar mass, what is dispersity and polydispersity coefficient. So these were discussed. The next lecture was on, again, it was on the concept of polymerization. So, molecular structure control, the goal of polymerization, and how does polymerization controls the tacticity or chirality, and the architecture of macromolecules, the sequence, branching, networking, and other architectures, and the quantitative control, like average molar mass or average segmental length, branching density, the length of the branch, and number of star branches. And then there was a discussion on step polymerization and polymerization of olefins. And the lecture 7 was on the sustainability aspect, the nature of bonding, the structure at multiple scales, like time and length scales involved in polymers, since the molecules are very giant. And then from macromolecules to small molecules, how can you depolymerize or de-crosslink in terms of sustainability aspect, right? And then the degradation of macromolecules, like scission of backbone, branches, crosslinks, and activation of degradation. The degradation can be a thermally activated due to heat, or through photolysis, or catalytic process, or enzymatic oxidation can cause, or hydrolysis, radiolysis can cause. And then what are the questions that are related to sustainability aspect of polymer? So the life cycle cost, degradation in a holistic manner. So as such, the polymer should not degrade during its performance period, whereas after its performance, it has survived for its service life. After its service life, it should degrade. And how to bring in the polymers into a part of biogeochemical cycles. So these aspects were discussed. So next was on is on week 2 lectures. So week 2 lectures were on simple concepts related to a single macromolecule. The lecture 8 was on renewable sources for polymers. So what are the sources of different sources of polymers, and what are the strategies for using renewable sources for polymers, and how can we incorporate natural fibers, and for natural fiber composites. Some examples of polymers from renewable sources: polymer from renewable monomer like your polylactic acid, or polymers that are polymerized by microorganisms like your polyhydroxybutyrate. So these were all discussed. Then lecture 9 was on polymerization, depolymerization. This was again on sustainability aspect of polymers. So polymerization method for each polymer were discussed, and then ionic polymerization, and how can we think of new ways about polymerization, and how can you control the molecular structure in case of like from biopolymers, and then in vivo and in vitro polymerization, and certain aspects of depolymerization. So these aspects were all discussed in lecture 9. Lecture 10 was on states of interest. So, unlike normal materials where you have solid, liquid, and gases, in polymers you have liquid like state, because there is still some kind of a solid like behavior that is there in the material, though the liquid like state will be predominant behavior. And then solid liquid like states, like in your case of your gels, and then solid like states. And then what are the molecular interactions and temperature, solvation, plasticization, uh, and liquid like states like polymer solution was discussed, polymer melt was discussed, and then solid liquid like state where polymer gel and liquid crystalline polymer was discussed, and solid like state like your rubbery, glassy, and semi crystalline polymers. So these aspects were all discussed in the states of interest. And then the application based terms were discussed in lecture 11. So types of polymer based on application, you have thermoplastics, thermosets, rubbers, and then polymers used in electronics, fuel cells, batteries, sensors and actuators. You have conducting polymers, and then ionic polymers, polyelectrolytes are there. Okay, and polymer charge complexes, dielectric elastomers, and then polymer solution, dispersion, gels, and polymer composites. So these were all discussed in lecture 11. Next, the lecture 12 again was on reuse and repurpose. So the linear and circular economy, okay, and then ecological and carbon footprint aspects were discussed. What are the aspects of reuse, and then carbon footprint reduction due to reuse and recycling. So these aspects were discussed in lecture 12. Lecture 13 was on molecular conformation. So, how does conformation comes into picture in case of a small molecule like ethane and butane, and how does it play a role in case of conformation in case of a polymeric or macromolecule like polyethylene. Role of conformation, the statistical properties of single macromolecule like length and direction vector of connecting first and last carbon atom were discussed, mean square end-to-end distance, and distribution of end-to-end, and orientation of ith bond. Okay, the orientation correlation. So when if you can you can have a better correlation for a nearby segments, whereas as the segments are much more, the orientation correlation actually decreases exponentially. So these aspects were discussed. And then size, mobility, and flexibility of macromolecules. So what are the statistical properties of single macromolecule, and the concept of ideal chain and freely rotating chain. So in freely rotating chain, in case of ideal chain, it is very similar to your ideal gas concept, where there is no interaction between the polymer molecule and its surrounding environment. Whereas in case of a freely rotating chain, you also bring in the hindrance due to your bond angle. And then next, use and application of single macromolecule models. The size of macromolecules in solution like overlap concentration, intrinsic viscosity, flexibility of macromolecular segment like rubber elasticity, swelling in polymer gel, viscoelasticity, and then the concept of radius of gyration, shape of macromolecule under shear and under charge, and then expanded chain where you have the excluded volume interactions were discussed, and then macromolecule as a Hookean spring and potential for a Gaussian spring and the force. So these concepts were related in were discussed in lecture 14. Lecture 15 was on complete discussion on polyelectrolytes. So from a simple electrolyte to a polyelectrolyte, the concepts were discussed, and then examples of polymeric systems with charges not as a part of the polymer molecule itself was also discussed, and then application of polymer electrolytes, sulfonated polymer in fuel cells where Nafion is discussed, and then the week 3 lectures. Week 3 lectures were on molecular arrangements and states of polymers. So the structure in biopolymers. So molecular structure of biopolymers, different structural levels like primary, secondary, tertiary, and quaternary levels, and then what are polynucleic acid? DNA is an example of a polynucleic acid, and then proteins. Here, the hierarchical structure of casein was discussed, and then polysaccharides, the role of polysaccharides was discussed, and then pectin was discussed in detail. And then lecture 17 was on amorphous and crystalline states. So this was on concepts. So the importance of semi-crystalline polymer, the features of crystals in atomic systems, and then crystallization in atomic system was discussed, and then macromolecules in crystalline form so was discussed, and then crystals observed in proteins was discussed, polycrystalline state of polymers. So where you start seeing the chain folding and then lamella formation and then spherulites are formed. So these aspects were discussed. The next lecture was on amorphous and crystalline states. This was again on concepts. So thermodynamic description of crystallization and melting, the first order transition, and then crystallization of polymers. What are the complexities involved in crystallization of polymers? And then inherent kinetic factors in polymers, the rate of crystallization and mixture of polymers, and what happens when there is a mixture of polymers and the crystallization aspects of those. So these were all discussed in lecture 18. So lecture 19 was on orientation and the molecules, crystallites, domains, and then fibers and fillers, the quantification of that, application, and then orientation, during processing. So these aspects were discussed in orientation. Lecture 20 was on interactions. So interaction of polymers at molecular scales, different type of interactions like non-covalent interactions, and then there was a discussion on hard sphere and square well and Leonard Jones potential, and then interaction in polymers, the coarse grain level and the empirical approach. So these aspects were discussed. Lecture 21 was on kinetics of crystallization, and then the glass transition and melting, polymer crystallization, structure and growth, like your nucleation and the growth of the crystals. So these aspects were discussed. So crystallization rate as a function of temperature, the thickness of lamella as a function of temperature, and then two crystallization model. One was Abrami model, and the other one, the Ozawa model. So these two models were also discussed. So the next lecture was on glass transition. So this was on properties. So what are the basic concepts related to glass transition? Getting to know about the amorphous states, properties in glassy states, and TG depends on the history also. And what happens when there is a glass to rubber transition? What is the dilatometry? Importance of glass transition. So these aspects were discussed in lecture 22. And the week 4 lectures were on polymeric materials of different kinds. So here the liquid crystalline polymers was discussed, and then the copolymers. So sorry, the liquid crystalline polymer was discussed. What are the free energy change, and then liquid crystalline polyesters, and then PET versus liquid crystalline polyesters, the aramid Kevlar. So these aspects were discussed. And then lecture 26 was on copolymers. Here, the homopolymer and copolymer. What is the difference between a homopolymer and copolymer? In homopolymer, it is a single type of monomer you could find, whereas in case of copolymers, two different types of monomers you can find, and these two monomers can individually polymerize as well. So here you have two different types of monomers, and how the sequence distribution varies, like your random copolymer or block copolymer, and how can polyethylene be a copolymer, and uh, you know uh, based on having different monomers, but still you will end up with the CH2 groups in the final polymer. And then silicone polyether, chitosan and chitin. So these were all discussed in copolymers 1. And then copolymers 2 was on properties. So controlled copolymerization for specific copolymers, different regimes of reactivity ratios, copolymers related to homopolymer, and then free volume and glass transition, combined behavior, crystallization, what happens in case of crystallization of copolymers. Because if one of the monomer is able to crystallize, but any other monomer is not able to crystallize, then crystallization is actually difficult in case of a copolymer. And then block and graph copolymers were discussed. And then lecture 28 was on blends. So, mixture of two or more polymers, melt blending, solution blending, reactive blending were discussed. Miscibility in polymeric systems, mixtures of A and B, and polymer solvent miscibility aspects were discussed. And then the lecture 29 was on blends again. It was on Gibbs free energy change due to mixing, Flory against theory for mixing of polymers, polymer blends and phase separation, critical temperature, and then glass transition of miscible blends, polymer blends were discussed. And then week 5 lectures were on physiochemical, mechanical, and electrical properties of polymers. So in lecture 32, the stress strain response, the mechanical response of polymers, the stress strain curves, the uniaxial tension, the static mechanical testing, what is a brittle polymer, ductile and flexible polymer, and then modulus, slope of stress strain curves gives you a modulus, and then tensile strength, toughness, the energy of absorption before failure. Right, the area under the stress strain curve gives you a toughness, and then description of polymers based on stress strain curves. And then the next lecture was on additives, examples of additives for polymerization. And then for processing, you add different kind of additives. And then for performance, you add different kinds of additives. And then for different properties, to enhance certain properties, to give some additional properties, there are some additives that are being added, stabilizers. And then there was a discussion on plasticizers, flame retardants, and then stabilizers like antioxidants and UV stabilizers, additives that have environmental impact. So these aspects were discussed in lecture 33. Lecture 34 was on blends and composites in recycling. So polymeric product, the life cycle. So this lecture was on sustainability aspects, and chemical recycling, mechanical recycling were discussed, and then heterogeneities in polymeric products, like as simple as you take your polymer packaging, there will be multiple layers, and each layer is made up of different polymeric materials and different additives for certain performance, for giving certain performance. So that makes this the recycling of polymers very challenging. And then plastic mix, and then polymeric materials recycled as blends and composites with biopolymers. So these were all discussed in lecture 34. Lecture 35 was on physical and chemical cross-linking. So cross-linking, there was basic discussion on types of cross-linking, like and then it may be a physical or chemical cross-linking based on the functionality, based on the polymer backbone reactivity, based on stimulus. And then covalent cross-linking was discussed, and examples of cross-linked systems, and then cross-linking in bio macromolecules. So these were all discussed. Lecture 36 was on mechanical properties. So the mechanical response, different modes and properties, what is the stretch ratio, and then elasticity was discussed, the linear elasticity, non-linear elasticity. In linear elasticity, it is based on the Hooke's law, where secondary interactions play important, and there's an energy spring. Whereas in non-linear elasticity, you bring in the concept of the entropic spring, the segmental mobility, and then uniaxial stretching in rubbers, and then non-linear elasticity. Simple models were discussed, like Monnier-Rivlin model and the Neo-Hookean model. And lecture 37 was on mechanical properties. So different types of mechanical response, like static testing, and then small deformation response and large deformation, uh, testing, and then dynamics testing for understanding viscoelasticity, and advanced mechanics of polymers, like your failure or fracture mechanics, fatigue, impact. And then there was a discussion on temperature and strain rate effect, post graining of macromolecular mechanism, and then time temperature superposition. Okay, so these aspects were discussed. The next lecture was on physical and chemical aging again. So aging process in polymers due to different effects. It can be physical or chemical aging. And then degradation of polyisoprene was discussed. Aging in wood due to aerobic, anaerobic and destruction, and identification of groups to identify the aging. So there will be functional group difference due to aging process, which can be identified using a technique called as FTIR, was discussed. And then property changes with aging, and then what is accelerated testing for predicting lifetime. Because for example, if your service life is going to be 40 years, you cannot test. And how does the material behavior change over the 40 years of time? You cannot do the testing keeping the sample for 40 years. So you do some accelerated testing where you give some stringent condition, so that you can as we saw in the time temperature superposition. Similarly, you can by giving some stringent condition, you can just superimpose and then find out what will be the actual service life of the polymer. And then the next lecture was on solution properties. So what is the overlap concentration, intrinsic viscosity, the theta temperature and solubility parameter, macromolecular solvent interaction, how does the macromolecular size plays a role, and then orientation and persistent length and persistent chain. So these were all discussed in solution properties of polymers. The next lecture was on conducting polymers. So intrinsically conducting polymers, that these polymers will have you know uh, uh, they have the conjugated bonds, that is the alternate single and double bonds. Okay, the electrical conductivity in polymers, the electronic conduction, and all polymer device where uh, the it will have components, the electronic components and everything will be made up of polymers only. And then what are the different applications? The next was on dielectric response. What is the linear? Here there was a basic discussion on linear and non-linear responses, and then complexities in response of polymers, and then energy storage and loss. And then the next lecture was on again on dielectric response of polymers. So response of materials due to electromagnetic radiation. There was a detailed discussion on dielectric spectroscopy, and then dipoles in polymers, and orientation polarization, molecular relaxation. Your D by relaxation was discussed in detail. The next lecture was on plasticity in polymers, the yielding, yield strain, strain softening and hardening were discussed. And then models of plasticity in polymers like your Eyring model and Ramberg-Osgood model were discussed. Lecture 44 was on properties of composites. So the shape, size, and type of fillers. How a premixed form for is easy processing. And then the composite properties as a function of constituent properties, your parallel and series mixing rules, and help in psi model was discussed. And then composite, how the amount, distribution, and orientation of fillers and reinforcement play a role, like your volume fraction of fillers, and how does it affect the processing, thermal or electrical conductivity of composites. There was a discussion on dilute system. The Maxwell model was discussed. Week 7, next, the week 7 lectures were on viscoelasticity in polymers. So the viscoelasticity, a basic introduction on viscoelasticity, what is a viscous response, elastic response, and then what happens in case of macromolecules. So you have a viscoelastic response, right? And then the contributions, their contributions, and then Deborah number was discussed, the terminal response was discussed, and then elastic, viscous, and viscoelastic response is a matter of time. And then polymer sample subjected to creep and recovery was discussed. And lecture 46 was on thermal response. So high temperature response for different polymers, and then thermal signatures, like and then annealing was discussed. And then there was a discussion on differential scanning calorimetry, TGA, TMA, and then DSC was discussed in detail, and thermal conductivity for polymers was discussed. And then lecture 47 was on viscoelasticity characterization. So the static test, the dynamic test, what are the theories and experiments, what the type of deformation, and how the sample geometry should be taken care of. And then there was a discussion on creep and stress relaxation of polymers. The lecture 48 was again on viscoelasticity. Simple models were discussed. And then when is viscoelasticity very important? What is the relaxation process? Linear viscoelasticity. Void model was discussed. And then creep response of void model, Maxwell model, and stress relaxation response of a Maxwell model were discussed in detail. Lecture 49 was on dynamic mechanical analysis. So the oscillatory testing, Maxwell model, model response, and then DMA. So different sample geometries with different fixtures were discussed. Rate and frequency, stress or strain control it can be, temperature control, and then what are the regions of viscoelasticity, different regions of viscoelasticity, your E prime and E double prime, how does it vary in different regions of viscoelasticity were discussed in detail. And then lecture 50 was on damping application. So energy dissipation during stress strain cycle, and then energy storage during stress strain cycle, and damping of vibration and sound absorption was discussed in detail. Viscoelastic response of rubber, and then there was a discussion on standard linear solid model and then damping materials. And then lecture 57, sorry, 51 was on time temperature superposition. So the linear viscoelasticity and this time temperature superposition can be done for the linear response part of it only. And integral statement of Maxwell model, Boltzmann superposition principle, viscoelasticity in polymers, and what are the temperature effects, time and frequency, temperature equivalence, shifting of data. How can you shift the data? For example, if you are doing at higher temperatures, and how can you shift the data in for a in a time scale was discussed in detail. And then lecture 52 was on impact and energy absorption. So high rate of loading, and energy and stress intensity, what is the failure process, energy under a stress strain curve, fracture energy, stress intensity factors, and then polycarbonate and ABS blend and alloy, and how does the property vary in this case of blend and alloy was discussed. And what are the different impacts in testing, like your ISOT test, Chappie test were discussed, and values for different polymers were also shown. And again, uh, a recap of lectures of week 8. So this was on viscoelasticity in polymers. So different testing for applications, like your trade tests were discussed in details, your hardness testing, what are the advantages, and different hardness testing examples, different methods for testing, and volume and surface resistivity. So these aspects were discussed. And then lecture 54 was on properties of blends. The glass transition temperature for blends and their miscibility was discussed. And then synergistic and additive effects in case of blends and copolymers were discussed. Okay, and toughening using rubber particles, and blends of conducting polymers. So these aspects were all discussed in lecture 54. Lecture 55 was on biomimetic polymers. So biomimetic devices and materials. Examples, biomimetic polymers, examples in lubrication, your synovial fluid, was discussed in this. And then can polymers be developed which mimic materials in biological organisms? Here collagen was discussed and its hierarchical structure arrangement was discussed. And the next lecture was on advanced mechanics. Here there was a discussion on mechanical analogs, basis of overall model, and then failure, the Griffiths hypothesis, crack growth mechanism, fatigue, and then there was a summary of the mechanical response that was discussed as well. And lecture 57 was on viscoelastic response examples, your master curves. So here creep complaints of polystyrene at different temperatures, and then master curve based on experimental measurements, and then dielectric response of polyvinyl alcohol, and viscoelasticity, the relaxation time at different measurements. So these were all discussed in lecture 57. And then there was a shift in topic in week 8 itself. So the discussion moved from viscoelasticity in polymers to interaction of polymers with other materials. Here, The polymer packaging, so uses, like examples of packaging applications, like your barrier films. Okay, it can be an oxygen barrier or humidity barrier, and then impact resistant packaging, secondary packaging, electronic packaging, renewable and biodegradable packaging. So these were all discussed. And then important phenomena associated to barrier films, right? Because barrier films means, for example, oxygen barrier means they should not allow oxygen to diffuse in. uh, and similarly, moisture barrier means your moisture should not diffuse in inside the packaging. So the diffusion, absorption, and then adsorption and leaching, so these concepts of permeation, and then properties of interest and thermodynamics and transport of the properties of interest were discussed. And then what is permeation and permeation rate for packaging material, so these were all discussed in polymer packaging. Next, porous polymers or membranes were discussed. So polymeric separation membranes, so different type of diffusions like your solution diffusion, Knudsen diffusion, molecular sieve, miscibility, processing to make porous membranes were discussed. And then polymeric foams were discussed, the types and distribution of pores, application, and then phase separation aspects, the blowing agents, and examples of polymers for foam. So these were all discussed. Lecture 60 was on polymers at interfaces. So interaction of polymers with other materials, so polymers at interfaces were discussed. So interfaces in polymers, polymer surfaces exposed to, so polymers can have different kind of interfaces based on the environment it is getting exposed. For example, if it is there in some solvent, then there will be an interface of polymer in the solvent. Or if it is your air environment, or it can be water, if it is exposed to some water or some moisture, so it can form an interface. So different interfaces are related to polymeric surfaces. And then polymer interface during processing, uh, so where it may have some interface with some solid, like in a mold. And then polymers in solution were discussed, interface for formed in a polymeric systems, and polymers in multi-layer or joint products, and difference between the bulk polymer and the polymeric interface were discussed. Macromolecules in thin films, so in case of thin films, the interfacial behavior becomes dominant because the thickness of the polymer itself, the film itself is very very small, that uh, you know more than the bulk behavior, the interaction with the interfacial response becomes much more prominent and dominant in the case of thin films. So this aspect was discussed. Surface energy of polymers, surface free energy, interfacial energy, and what are the manipulations, so these were all discussed. Lecture 61 was on diffusion in polymers. The Fick's law, and then diffusion of water. Diffusion in liquids and crystal solids were discussed. Crystalline solids were discussed. And then the liquids, the Brownian motion, the Stokes-Einstein relation, and solids, the hopping through the crystal lattice for diffusion to take place. And then the random steps in case of solid diffusion, which is very similar to a random box in molecule, in macromolecules. And then what happens when there's a variation in temperature. And then the concept of free volume and diffusion of small molecules in case of macromolecules was discussed. And then combination of activated and free volume diffusion. And then diffusion in case of a semi-crystalline polymer. So diffusion becomes much more complex in case of semi-crystalline polymer because of the associated uh, crystallinity in the polymer, right? So because molecule cannot easily diffuse when you have some crystallinity involved, it cannot pass through this lamella or this ferrulate so easily compared to an amorphous polymer. Okay. And then again, next, the week 9 lectures, this was again on interaction of polymers with other materials. Here there was a detailed discussion on compatibilizers in lecture 62. So compatibilizers for blends, the role of compatibilizers, the type of compatibilizers, the reactive compatibilization, and then fiber treatment and sizing, the surface treatment, coupling agents and sizing of fibers, the components for sizing of glass fibers, the role of sizing in fibers were all discussed. So the natural fibers and polymers like cellulosic, which is hydrophilic fibers, and the hydrophobic polymers. How the compatibilization becomes a critical phenomena here. And then compatibilizers, the sizing, which is a key for mixed waste plastic recycling. So this aspect was also discussed. Then the lecture 63 was on biopolymer applications. So here there was a detailed discussion on two different polymers. One was on xanthan gum, the other was on polyisoprene, which is nothing but your natural rubber. So xanthan gum, how the interaction plays, a very important role, in its behavior and in its application and its usability. Whereas in case of rubber, it's more of an ideal system where there is no interaction. The interaction does not play a critical role in its application. For example, as a elastomer or as a vibration mount. So these two, extreme aspects in these two different polymers were discussed in detail. And then lecture 64 was on adhesives and paints. Okay, the application, so structural adhesives, the mechanism of adhesion, and then the adhesion formulation, and then adhesive failure, like cohesive and adhesive failures. So these were discussed. And then paints were discussed in detail. The components of paints, what are the components and coatings, and the role of polymers, water-based paint, the associative thickness were discussed in detail. Next, the topic shifted from interaction of polymers with other materials to polymer processing and recycling technique. Okay, and lecture 65 was on dissolution and recovery. So this was on sustainability aspect. So mechanical recycling, the process and challenges in mechanical recycling, and then what is a chemical recycling, and what are the process, and what is the CO2 equivalent emission for different chemical recycling process were discussed in detail, and of which this dissolution phenomena, it had very low CO2 equivalent emission, so which is very, very promising aspect, right, for recycling of polymers. So macromolecular recycling through dissolution. So examples and recover. How do you recover solvent? Because again, in dissolution you use a solvent. So if you going to use some toxic solvent, again it is going to be an environmental impact. So how can you move to some sustainable solvents, or non-toxic solvents, some ionic solvents were discussed. And then what is the dissolution rate? So what happens when you have a amorphous polymer exposed to exposed to a solvent, you will start forming different layers, and then dissolution in amorphous polymer, and then the concept of anomalous diffusion in polymers, and there was also a highlight on dissolution in case of a crystalline polymer as well. And what is the difficulty in case of again crystallinity comes into picture in case of dissolution also was discussed in detail. And then lecture 66 was on polymerization kinetics. Polymerization operation, and what is polymerization processing, the reactive processing, what is the aspects of composite processing were discussed. And then what is the kinetics of free radical polymerization, step growth polymerization, and of living polymerization were discussed in detail in this lecture. The next lecture was on polymerization reactors. So mode of polymerization. What are the different modes of industrial polymerization? You can have bulk polymerization, solution, precipitation polymerization, suspension, emulsion polymerization, or even gas-phase polymerization. And then there was a discussion on polymerization of LDPE, HDPE, and polypropylene and polystyrene, and there was some brief discussion on other examples for different polymers as well. Lecture 68 was on polymer processing. So here, what are the different unit operations involved? What are the tooling requirements? Processing techniques? What are the flow behavior? And then liquid crystalline polyester was discussed. And then processing and properties determined by molar mass. What is the milk flow index measurement? And what are the different dimensionless number associated with polymer processing? Like you have your Deborah number, Weisenberg number, and then Reynolds number, and then elasticity number. So these were all discussed in polymer processing 1. Polymer processing 2, there was a detailed discussion on the extrusion process where single and twin screw extruders were discussed, and then extruder characteristics, what are the extruder variables, and then die opening and pressure drop was discussed. And then the next process that was discussed was on injection molding. What is the operation? What is the processing window for an injection molding process? And then analysis of processing operation. Like you are having ideal flow, and then what are the the polymer has to pass through complex geometries. What are the phase change that may happen? The heat and mass transfer associated, the reaction that is going to happen. So these were all discussed in polymer processing 2. And then polymer processing 3 was discussed in Vigen, and the shaping operation, extrusion dies, and then stretching, rolling, blowing was discussed. Blow molding was discussed in detail. Time scales for polymer processing. What is the cycle time for different polymeric operation? What is the production rate? You have very short time scales like in injection molding and all. So these were all discussed. And then mixing in polymeric systems, mechanism of mixing, you will have more of a laminar flow in case of mixing of polymers. So the mixing will be a little difficult process. And then what are the different mixing operations? So these were all discussed. And then the next lecture was on flow simulation. So modeling of polymer processing. So it's a multi-scale phenomena. What is the continuum description, molecular description, what are the transport phenomena involved, and then molecular dynamics, the need for modeling and simulation. And then there was a discussion on mass balance and conservation of mass, and then conservation of linear momentum, your Newton's second law, and then conservation of energy, and then enabling polymer simulations, and what are the polymer simulation softwares. So general simulation softwares, and also some industry or particular process oriented simulation softwares were also discussed in detail. And then processing for recycling. So the recycling methods, the primary and secondary recycling, recovery and conversion. What are the targets in Indian national resource efficiency policy was discussed. And then operations that are, so before you are actually going to recycle the polymers, there are certain operations that you recycling operations you have to perform. And then what are the pre-processing and processing conditions for recycling, and what happens to properties due to recycling of material. So these aspects were discussed. And then lecture 73 was on recycling up down cycling. Okay. And what are the waste handling in India, what are the challenges involved in that, and then additional challenging during mechanical recycling. And then polymer processing, the complex transport phenomena involved, what are certain upcycling process. And then what is the mechanical chemical upcycling, so designed for recycled polymer materials. So and then upcycling through blending of polypropylene with LDPE. So this was discussed in detail. And the next lecture was on recycling up down cycling again. So biocomposites was discussed, and then twin screw extruder, polymerization and molding, the reaction injection molding process was discussed, resins transfer molding, the biocomposite sandwich structure was discussed. These aspects were discussed in this lecture. The next lecture was on flow behavior. So obviously when you are having a polymer processing operation, there will be different flow that is happening. So the concept of rheology was introduced. So polymeric fluid flow. So what happens when a polymeric fluids as products, and then polymeric fluids in processing of polymers and composites. So this was discussed. And then macromolecular in flow, So classifications based on flow behavior, mechanism that affects the flow of macromolecular systems, the non-Newtonian fluids were discussed, the flow scenarios, what is the response of macromolecules in different flow scenarios. So these were all discussed in lecture 75. And then lecture 76 was on cross-linking. Here there was a discussion on step growth and chain growth polymerization, the extent of cross-linking for step growth polymerization, and cross-linking in rubber, the curing time. And there was a discussion on oscillatory disk rheometer and moving die rheometer. And then cross-linking and gelation related to viscoelasticity. So this was discussed. Lecture 77 was on conversion of polymers. So this was on sustainability aspects of polymers, conversion and combustion of polymeric materials, the chemical recycling, factors affecting conversion of macromolecules, the rate of conversion, the role of absorption and diffusion, and then chemolysis was discussed. Chemolysis of PET, that is converting PET to its monomers. So how do through different chemolysis techniques, you end up with different monomers of PET was discussed, and then conversion to feedstock, and then combustion and incineration of polymeric materials was discussed. Lecture 78 was on rheology and entanglement. So rheology, the study of deformation behavior of fluids. So shear and extensional rheology was discussed, and then one-dimensional flow, the narrow gap necessary for the rheological studies, and then the controlled variables, polymer processing, the large deformation involved, and the non-linear rheology involved. What are the rheometry geometry for rotational rheometer, the thin gap, and then different geometries like cone and plate, parallel plate, concentric cylinders were discussed. And for which kind of polymers each of these are used, their pros and cons were discussed. And then oscillatory shear response of a polymer build was discussed. And then extensional flow in branched polymer, the strain hardening was discussed. And then fiber orientation, what happens in case of shear and extensional flow, where you will have a better fiber orientation was discussed. And then lecture 79 was on rheological models. This is the class of models like linear viscous, non-linear viscous models, which is a generalized Newtonian fluid, and then linear viscoelastic fluids, and then shear thinning models. Your Carrier-Yasuda model and Herschel-Buckley model. So in your Herschel-Buckley model, you have your this applies for a shear thinning systems where actually you start seeing shear thinning after there is a the material crosses a yield stress. After crossing the yield stress only you will actually see the flow in such kind of materials. uh, and then there was a discussion on non-linear viscoelastic model, the Pantheon Tanner model, the convected derivatives was discussed, the frame indifference, and the material objectivity. So these aspects were discussed. And then lecture 80 was on rheology and processing. So mixing in different flows, laminar mixing, the simple shear flow, the linear material point separation, and in case of extensional flow, you have the separation between 2 points becomes exponential. Okay, and then viscous dissipation was discussed, and then dye or extruded swelling, because this happens because of the stretching and orientation when it passes through the dye, and once it comes out of the dye to the outside, there is a recovery and recoiling. So this causes a dye or extruded swell. What happens because of this? So the material coming out will not have the same size or shape as that of the your dye, because of your stretching and orientation as it passes through the narrow opening, and then the recovery process once it comes out of the dye. And then the entanglement and reptation was discussed, the correlation with rheological properties, the influence of normal stresses was discussed, and then rheological and interfacial properties were discussed, and then deformation in a simple shear flow, the velocity gradient, the strain rate tensor, stress tensor was discussed, the Newtonian and generalized Newtonian fluid was discussed, the stress tensor in case of simple shear flow for viscous fluids and viscoelastic fluids was discussed. the deviatoric stress tensor, the normal stress difference, and then different techniques of rheology like your rotational rheology, tube flow, and then extensional rheology. What are some trade test of rheology? So these were all discussed in this lecture. The next lecture was on uh, absorption and leaching. So, what are the fate and transport of polymers in environment? So, because of its low density and less level of biodegradability, it has a long life, and because of its low density, it can for example, in a water surface, it can flow through long distances. Okay, and what happens in case of exchange of small molecules? So, small molecules can get absorbed into the polymers, and also similarly for example, when you have a polymer having a plasticizer in it, these plasticizer small molecules can leach out of the polymers also. So both of these will have an impact on the environment. And then thermodynamics of solute exchange, the solubility, partitioning, sorption isotherm, kinetics of solute exchange was discussed. And then absorption kinetics, what is the Fickian, non-Fickian diffusion, case 2 diffusion was discussed. And then leaching and leaching kinetics was discussed in this lecture. The next lecture was on spelling of polymers. So spelling of cross-linked polymers. So solvent with linear or branched polymers, you end up with polymer getting dissolved. Whereas in case of cross-linked polymers, the polymers doesn't get dissolved because of the cross-linking present, and it ends up in swelling of the polymers. And the equilibrium between the osmotic pressure and chain elasticity was discussed. Uh, the Flory-Reiner equation, and then applications of the spelling like in superabsorbent material, like in your diaper, and then how can you measure the cross-link density, and then what is the hydrogel, organogels, the Flory-Huggins theory and the network elasticity was discussed, the swelling ratio based on the weight and volume, the osmotic pressure, which is nothing but change in delta G, and then your network elasticity based on ideal chain model entropy based was discussed. The Flory-Reiner equation was discussed. The kinetics of swelling, the mass transfer, large deformation and relaxation associated were discussed in this lecture. The next lecture was on viscosity for polymer processing. So here capillary rheometry was discussed in detail. And then the Hagen-Poiseuille equation and what happens for a Newtonian fluid. Whereas in case of in case of viscoelastic fluid, uh, you don't have a Hagen-Poiseuille equation, whereas you have to use equation of motion. And then the developing flow, entrance effect, and the Bagley correlation was discussed. Maximal model, the sinusoidal input and model response was discussed. And then the final week lecture, the week 12 lecture was on polymer and environment. So the first lecture of that week, lecture 84, was on microplastics, aerosols, and then sediments. The fate, and again here there was a discussion on fate and transport in polymers, and then release in environment, sizes and origin, the impact of microplastics. What are microplastics? What are its impact and different interactions with the surroundings and their prevalence were all discussed. Lecture 85 was on biodegradation of polymers. So degradation of polymers in environment. So exposure to environmental condition and light, there will be some degradation. Due to thermal effects, there will be degradation. Mechanical effect, there will be degradation. And then the concept of biodegradation was discussed in detail. And then what are the factors involved in biodegradation? And then what are biodegradable polymers and polymeric waste management. So these aspects were discussed. And then lecture 86 was on biodegradable polymer 1. Here polymers with biological relevance was discussed. What are the different degradation claim, and then what is composting, and then biodegradation of polyhydroxybutyrate and polylactic acid and starch based polymeric system was discussed. And lecture 87, which is the last lecture of the course, this was again on biodegradable polymers. Here application and processing was the main aspect of discussion, and most promising application of starch, polyhydroxybutyrates and alkonates and polylactic acids were discussed. What are the biodegradable polyesters and how can you think of biodegradable thermosets and elastomers? So these aspects were all discussed in the lecture. Now let's get on to the practice assignment session. Question number 1. There are two different PTFE polymer specimens of the following density and percentage crystallinity. For PTFE specimen 1, the density is 2.144 gram per centimeter cube and percentage crystallinity is 50. For PTFE specimen 2, the density is 2.215 gram per centimeter cube and percentage crystallinity is 75. So assuming the polymer is pure and defect free, the density of 100% amorphous PTFE will be. So what will be the density of PTFE if it is 100% amorphous? So this is what is the question. This is a GATE 2021 question. So what are the points given? So they have given two specimens of PTFE. Specimen 1 having a density of 2.144 and crystallinity 50%. So fraction of crystallinity is nothing but 0.5. And specimen 2 with the density of 2.215 and percentage crystallinity 75%. So fraction of crystallinity is 0.75. So you have a relation fraction of crystallinity is equal to rho minus rho A by rho C minus rho A, where your rho A is your density of amorphous phase, rho C is your density of crystalline phase, and rho is your total density of the specimen. Okay, so from this we can find out what is the density of amorphous phase. For example, for specimen 1, so rho C1 is equal to rho S1 minus rho A by rho C minus rho A. So you have rho C1 as 0.5 and the total density of the specimen is 2.144. So substituting that, you will end up in this equation. Similarly, for specimen 2, you have 75% crystallinity. So your 5C is 0.75 and your rho S2 is nothing but 2.215. So you have now two equations. Okay. So from these two equations, you can find out what is the density of the amorphous polymer. So how can you find out? So if we divide the equation, because there are two unknowns also. So you have your crystalline phase density is also unknown and your amorphous phase density is also unknown. So what you can do in this equation? So if you divide equation 1 by 2, what you will get? So you will get the denominator in both the cases will get cancelled out. And then you will have 0.5 by 0.75, that is equal to 2.144 minus rho A by 2.215 minus rho A. Okay. So because for both these specimens, the amorphous phase density and your crystalline phase density will be the same. Okay. Only because of the fraction of crystalline phase and amorphous phase difference, the overall density is changing. Okay. So just cross multiplying it, you will get 0.5 into 2.215 minus rho A is equal to 0.75 into 2.144 minus rho A. So you will end up with what is the density of the amorphous phase. So density of amorphous phase is 2.002 gram per centimeter cube, which will be the, so if you have 100% amorphous polymer, so this will be the density of the 100% amorphous PTFE. Okay. Next question. Match the polymers to their family. So you have polyurethane, polyamide, polyether, polycarbonate and polyester. So you have their structures also given. Now we have to match each of these. So which system will have a chain connected by O, C double bond O, O. So let's start with and then which will have NH C double bond O, and which will have O, and which will have C double bond O, O, and which will have CO and NH groups. So now for polyurethane, it will have a NHC double bond O, O group. So this family of polymers are called polyurethanes. Okay. In case of polyethers, you will have COC bond. Okay, this chain will have a COC bond. So these family of polymers are called polyethers. Okay, example is a polyethylene glycol. Okay, the next is polycarbonate. Polycarbonate will have OC double bond O in its structure. This kind of a say structure in its chain. So this belongs to polycarbonate. And your polyester will have COO group. And finally, your polyamide will have CONH, C double bond O NH group. Okay, next. Sorry. According to Stokes-Einstein relation, radius of gyration Rg is directly proportional to diffusion coefficient. Identify if the statement is true or false. So it is actually false. Stokes-Einstein relation gives that your diffusion coefficient is inversely proportional to your radius of gyration. Okay. Two miscible polymers A and B are blended in the weight ratio of 30:70. If the glass transition temperature Tg of polymer A is -50 and that of polymer B is 100, then the glass transition temperature of the blend is dash. This is a GATE 2012 question. So we have a polymeric blend of A and B where A is 30% and B is 70%. And we also have the glass transition temperature of polymer A, which is -50 degrees, and then glass transition temperature of polymer B, which is 100 degrees. So now what will be the glass transition temperature of the blend is the question. So how to go about this? So Tg of polymer A is -50 degrees, Tg of polymer B is 100 degrees, weight ratio is 30:70. Now you can use the Flory-Fox equation. So Flory-Fox equation gives the relation of the for the Tg of blend based on the weight ratio of individual polymers and the glass transition of individual polymers. So it is given by 1 by Tg is equal to W1 by Tg1 plus W2 by Tg2, where W1 and W2 are the weight of the polymer 1 and 2, and Tg1 and Tg2 are the glass transition temperature of polymer 1 and 2. So weight ratio of polymer 1, weight fraction of polymer 1 is 0.3, Tg is -50. So here for Flory-Fox equation, you have to convert your glass transition temperature in degree centigrade to Kelvin. So when you convert from degree centigrade to Kelvin, so -50 degrees, so you will get your in Kelvin it is 223.16, and similarly for polymer 2 the weight fraction is 0.7 and your Tg is again 100 degrees. So to Kelvin it is 100 plus 273.16, you will end up with 373.16 Kelvin. Okay, now substituting the values, you will get 1 by Tg is equal to 0.3 by 223.16 plus 0.7 by 373.16, and then simple mathematics, you will end up with Tg of blend to be 310.54 Kelvin, that is 37.4 degrees centigrade. So so one of the polymer had very low glass transition and another polymer had very high glass transition temperature, and when these two polymers were blended, the glass transition is somewhere in between, right? Next, entropic contributions in case of mixing of macromolecules is minimal. Identify how from the Flory-Against theory of mixing of polymer A and B. So we have to find out why is the entropic contribution in case of mixing of macromolecules is minimal based on the Flory-Against theory of mixing of polymers. Okay. So entropic contributions of mixing, for mixing of polymer, the contribution of entropic part is very less. So we have to find why is it less based on the Flory-Against theory. So this is what is the question. So, so delta G of mixing. So based on flow reagents theory, you have RT into NC, phi A by Na into ln of phi A plus phi B by NB into ln of phi B plus chi into phi A phi B. Okay. So from the delta G of mixing, the first term of this is the entropic term and the second term is the enthalpic term. Okay. And in the entropic term, we have phi A and phi B, which denotes the volume fraction of polymers A and B. Okay. While Na and Nb, it denotes the degree of polymerization. Okay. So, degree of polymerization, we know in macromolecules in polymers, it is the value is higher, right, compared to your volume fraction. Volume fraction is nothing but your fraction, right? It's a decimal number, right? So, obviously, your denominator is or your degree of polymerization is a higher value, or your denominator here in this case is a higher value. So you end up with the value of this entire term to be very small. So mathematically this term is very small. So this implies that the entropic contribution for mixing of two macromolecules is very small. Okay. Next. Identify true or false. Compatibilizers decrease the interface thickness. Is it true? Do they decrease the interface thickness? It is actually false. The compatibilizers helps in increasing the interfacial thickness. The action of compatibilizers, they increase the interfacial thickness from 40 to 60 nanometers. So this was discussed in one of the lectures. So as you can see in the image, the interface in the presence of compatibilizers, instead of having when it is a incompatible set of polymers, you will have a very small interface here. Okay. Whereas when in the presence of compatibilizers, this entire region, the instead of very small level of interfacial thickness, the interfacial thickness increases to somewhere between 4 to 60 nanometers. Okay. So compatibilizers actually increases the interfacial thickness. Okay. So there is much more of a mixed area. Next question. For a polymer which follows Mark-Hovenk equation, the various parameters determined were as follows. K is equal to 1.22 into 10 power minus 4. Your viscosity is 2.4. Your A is 0.7. Your Huggins constant is 0.33. And concentration C is 0.3 gram per deciliter. Okay. Now, from this given set of information, we have to find out what is the molecular weight of the polymer. Okay. And the next question is what is the specific viscosity of the above polymer? So these are the two questions that are asked. This is again a GATE 2008 questions. So they have also given different options for the molecular weight, whether is it 4.5 into 10 power 5, or is it 6.1 into 10 power 4, or is it 3.2 into 10 power 6, or is it 7.9 into 10 power 5. So which one of these is the right answer for the molecular weight of this polymer? Okay. And the second part is the specific viscosity of the polymer. Is it 0.73, or is it 1.12, or is it 0.89, or is it 2.3? So this is what is the question. Answer is, so your Mark-Hovenk equation, it gives, you get the relation between your viscosity and your molecular weight, which is given by eta is equal to K into M power A, where M is your molecular weight. Okay. And they have given what is the value of viscosity, which is 2.4. And then what is the value of K also they have given. They have also given what is the value of A. So from this, just rearranging it, you can get the molecular weight. Your molecular weight M is equal to eta by K the whole power 1 by A, which is nothing but 2.4 divided by 1.2 into 10 power minus 4 the whole power 1 by 0.76. So you will end up with 4.5 into 10 power 5 as the molecular weight of the polymer. So option 1 is the answer for question number 7A. Next, Huggins equation. So we have to find out what is the specific viscosity. So Huggins equation gives the relation between the the specific viscosity, concentration, and your intrinsic viscosity. So uh, your specific viscosity by concentration is equal to eta plus Huggins constant into viscosity square into concentration. Okay. So you have the value of, again, your concentration. It is given 0.3 gram per deciliter. Your Huggins constant is also given as 0.33. So from this you can and you also have the value of viscosity, which is 2.4. So specific viscosity you can find out. So just you have to take this concentration into the right hand side. So it is eta into concentration plus Huggins constant into eta square into concentration square. Okay. So which is nothing but 2.4 into 0.3 plus 0.33 into 2.4 square plus into 0.3 square. So you will end up with the specific viscosity of this polymer as 0.89. Okay. Next question. For mechanical analog elements, elements in so considering mechanical analog, okay. So mechanical analogs in parallel. When the mechanical analogs are in parallel, dash is equal. Is it stress which is equal, or is it strain which is equal? If we know different mechanical analogs. For example, for an elastic component it is a spring, for viscous component it is a dashpot. So if these two components are in parallel, or so which of the parameter is equal for this parallel arrangement, whether strain is equal or stress is equal? So it is actually strain is equal in this case. So you can see here a system where different mechanical analogs are arranged in parallel. For example, here you have some dashpot and spring which is arranged in parallel to another spring which is arranged in parallel to another a plastic element and your one more spring. So in this system, so your for 1 2 3, if you consider this series arrangement of dashpot and spring and the spring, so series arrangement of this dashpot and spring as system, uh, element 1, and your this spring as component 2, and this sliding element which is for plasticity, and your spring, the series arrangement of this sliding element and spring as the component 3. So for these three components your strain is equal. Okay. So the extent to which they get extended will be equal. The total strain in each of these elements will be equal. Okay. Whereas when you have a series arrangement, for example, if you have a see, for example, in this system 1 where you have a dashpot and spring arranged in series, so here your stress applied is equal. Okay. The stress sigma 1a is equal to sigma 1b. Okay. When there is a series arrangement, the stress is equal, whereas in case of parallel arrangement, the total strain is equal for each of the component. Okay. Which are arranged in parallel. Next question. The behavior of polymer is described by Maxwell model, consisting of a spring element of modulus 10 power 10 Pascal in series with a dashpot of viscosity 10 power 12 Pascal second. In the solid, 50 seconds after sudden application of fixed strain of 1%, the stress will be dash into 10 power 7 Pascal. So this is a GATE 2021 question. So we have a polymer, which can be described by a Maxwell model. Maxwell model is nothing but your spring and dashpots are arranged in series. Okay. And they have given the spring has a modulus of 10 power 10 Pascal and your dashpot has a viscosity of 10 power 12 Pascal second. Okay. Now they are saying that 50 seconds after sudden application of a fixed strain of 1%, what will be the stress? So given polymer material behaves as per Maxwell model. Okay, so Maxwell model, you have a spring and dashpot arranged in series, and your overall, your stress across each component is equal since it is a series arrangement, whereas your strain varies in each of the component. Okay, so your equation for Maxwell model is sigma plus lambda into uh, dou sigma by dou t is equal to eta max into E dot. That is nothing but your sigma is your stress and lambda is your relaxation time, and your dou sigma by dt is your stress rate, eta max is your viscosity of your dashpot element, and E dot is your strain rate. Okay, now they have given the modulus of the elastic element or your spring is 10 power 10 Pascal, and your viscosity of your dashpot is 10 power 12 Pascal seconds. They have given a time of 50 seconds, and then they have given a fixed strain of 1%. 1% means your actual strain will be 1 by 100, that is equal to 0.01. Now we have to find out what will be stress. Okay, so they have given sudden application of fixed strain, and then it is released, right? And then they have asked for what will be the stress uh, after 50 seconds. So there's a, sorry, the strain is not released, there is a sudden application of fixed of a strain of 1%, and then this strain is maintained for the rest of the time. Now they are asking what will be the stress after 50 seconds for maintaining this 1% strain. So this is nothing but your stress relaxation response. Okay, your stress relaxation response for Maxwell model is sigma of t is equal to E max into E naught into exponential of minus t by lambda. Okay, your Emax, they have given the modulus of the elastic component, which is your spring, which is 10 power 10 pascals. Your E naught, that is your fixed strain that has been applied is 1%, that is nothing but 0.01. And then they have also given the time at which you have to find out the stress, that is 50 seconds. You can find out the relaxation time, which is lambda. Lambda can be is given by eta by E max. So that is 10 power 12 by 10 power 10. That is 100 seconds. Okay. So here what is the case? This, why do you say this is stress relaxation response? Because you are applying, you're suddenly applying a strain of 1%, and then you're maintaining that strain of 1%. So in order to maintain that 1% strain, what will be the stress requirement over the time? So obviously, in order to maintain the same strain, the stress requirement will start decreasing over time. Okay, that is given by this exponential decay equation. Okay, for the stress. So now we have to find out what will be the stress at 50 seconds. Okay, so sigma at 50 seconds is equal to E max, which is 10 into E naught, that is your strain, which is 0.01 into exponential of t, exponential of minus t, which is nothing but 50 seconds divided by lambda, which is nothing but 100. So substituting all, you will end up with the strain, your stress at 50 seconds is 6.07 into 10 power 7 pascals. So 6.06 into 10 power 7 pascals. Okay. Next. The following figure shows scales of hardness for different class of materials. So you could find, you could see, the Shore, Shoddy and Rockwell hardness for different classes of materials like your elastomers, thermoplastics and thermosets. Okay. Now, state whether the following statements are true or false. Higher number on these scales implies higher hardness. Is it true? The second question is, elastomer of Shore hardness of 30 has a higher modulus than elastomer with Shore hardness of 90. Is it true? So Higher number on the scale implies higher hardness. Is it true? Yes. Higher the number on the scale, then higher is the hardness. For example, for these elastomers, if a particular elastomer has value of 20 and another elastomer has a value of 30, then the elastomer having value of 30 has higher hardness. Okay. Increasing values, increasing hardness. Now the second question is, elastomer of Fourier hardness of 30 has a higher modulus than elastomer with a Fourier hardness of 90. Is it true? There's a material having a lower hardness will have higher modulus or not. It is actually false. So a material having a higher hardness, that is the material having a Fourier hardness of 90 will only have a higher modulus compared to your material having a hardness of 30. Okay. So higher the hardness, higher the modulus will be. Okay. So these hardness values are all Fourier, Shorty, Rockwell are all your trade test values. Modulus is your material property. Okay. Sorry. So identify if this statement is uh, true in the case of polymer composites. Ease of processing increases with size of the fiber. So in case of polymer composites with reinforced fibers as a reinforcement, if the fiber length is higher, then it is easier to process such polymer composites. Is it true or is it false? It is actually false. So your ease of processing actually decreases as the length of the fiber increases. Okay. So if we start having long fibers, then what happens is, how do these long fibers orient during processing? How do these, they flow, and will these fibers get entangled with each other, or what happens to the viscosity of the system at so these all becomes questions. So the complexity is involved with the higher fiber length increases. Okay. As the fiber length increases, so that means the processing becomes more and more challenging. Next question. Ductile polymers are characterized by, actually the answer is there in the slide itself. They are characterized by yielding. Okay. So, your ductile polymers, your thermoplastics, uh, they are characterized by yielding. So this is your yielding behavior. So there's a permanent, structural change that is happening, but still the material does not fail. It fails, after there is some permanent change also. Okay, it still continues, withholding the strain after some permanent change also. So the ductile polymers are characterized by yielding. Okay, whereas in case of your brittle polymers, they have a failure at lower strains. So there is a failure. Okay, there is no yielding, it just fails. Whereas in case of flexible polymers, you will have very large deformation. So this is what is the case for a brittle, ductile and flexible polymers. And your ductile polymers are characterized by yielding, which is nothing but your plastic behavior. Okay. So there is some associated permanent change in the structure of the polymer. Okay. That's all with the session. Thank you.